Hi, everyone. You can tell I'm a Berkeley local. It was business casual attire, and this is the high end of business casual attire in Berkeley. We're still waiting for the display to come up. I was chatting with someone while we're waiting for the display, and they said, oh, Lawrence Berkeley, I haven't heard of Lawrence Berkeley, and so let me promote my institution. Just up the hill, there's a national laboratory, Department of Energy National Laboratory of 4,000 people doing energy research. Part of that institution is doing supercomputing. So the NERSC Supercomputing Center there provides cycles to energy researchers across the country. And so that's my angle here. I'm a visualization guy and also a visualization guy for supercomputing. Perfect, and the display is up. Thank you. So let's see. So I very much agree with our last speaker about viz porn and that's not the phrase I'd use, but it's a good phrase, and the value of visualization. And so here I've got a lot of it up on display because we were actually encouraged to bring some pretty pictures and movies so people could see what we're talking about. But I actually agree entirely. The reason that we do visualization is we want to help people understand their data, and making pretty pictures is just one piece of that. So let me start my movie going. So let's see, let me tell you what we're looking at here. In the bottom left, this is a simulation of a nuclear reactor. They're actually just simulating the coolant. So each one of these gaps here is a pin, and they're simulating the coolant around those pins, essentially making sure that here you can see actually where the coolant is, making sure that the coolant is flowing around and communicating well to actually cool down the pins and make sure that no pin gets too hot, a particularly relevant problem given what happened in Japan over the last 2 months. In the lower right, is a visualization of streamlines. And so the idea here is there's a simulation of a jet, and here we're looking at what's being expelled from the jet. And the idea behind streamlines is that you put particles in some location, and here we're putting it right where the material is being expelled, and you advect the location of those particles, i.e. you move it based on what's happening in the velocity of the simulation to kind of inform what's going on in the turbulent flow. And so you can see that most of it's being expelled out, and then it starts moving around as it gets further away from the jet. In the upper right is an astrophysics simulation, so that's a type 1a supernova. The orange surface is the flame front of the star, and then the blue area is the region where it's going to light on fire next. Up here on the upper left is an environmental simulation. So you can actually see, so this is doing a volume rendering, which is a visualization technique that uses a combination of transparency and color to show what's going on in the entire volume. And you can see where there are ecological problems, where there's pollution. And then the one in the top there is a Rayleigh-Taylor instability, and it uses really 2 common visualization techniques. One is to cull away what you don't want to see. So this is a simulation. A Rayleigh-Taylor instability has a heavy fluid mixing with a light fluid, and gravity pulls the heavy fluid down. And so what we're looking at here is just the mixing region. We took away all of the pure heavy fluid on the top and all of the pure light fluid on the bottom, and we can see what remains is where it's mixing. And so culling things away is a very common visualization technique. The other common visualization technique on display, and this image is what's called false coloring or pseudo-coloring, where we're mapping scalar values, in this case the amount of mixing going on, to colors. And so areas that are blue are light fluid, and areas that are red are heavy fluid, and then the regions in between are where the most mixing is occurring. Okay, so there's our, I don't even want to repeat, viz porn, I guess, but there's our pretty pictures. The problem here is that when you're doing supercomputing, you're generating really large data sets. And there's a question of how are you going to be able to visualize and analyze and understand those data sets. So supercomputing 101. People are doing simulations on supercomputing. Why are they doing simulations? They're often more cost effective than experiments. So if you're going to build a $1 billion nuclear reactor, and you can simulate the best way to design that reactor and do it before you break ground, that's a great return on investment. And then other situations, you don't even want to run the experiment. If you're talking about climate change, the experiment of running 1 billion cars around the planet for 50 years, the cost of running that experiment is really high. And if you can simulate climate change before it happens, wow, what a win. So the people that do simulation say that there's a new model for science where the previous model was a balance between theory and experiment. The people that are into simulation say there's now 3 legs: theory, experiment, and simulation. So how do we measure supercomputers? I think everyone agrees it's the worst way you can imagine. We measure them based on flops, which is the number of floating point operations you can perform in a second. So then a gigaflop is 1 billion flops. This laptop here can do a gigaflop. A teraflop is 1,000 gigaflops. That was the great milestone of 1998. A petaflop is 1 million gigaflops. That was the milestone of 2009. And believe it or not, everyone's now talking about an exaflop, which is a billion flops, 10 to the 18th flops, and that's supposedly going to be the milestone of 2018. So when people are talking about petascale computing, they're talking about having petaflops on a computer, petabytes of disk, and probably on the order of tens of petabytes of memory. When people are talking about exascale computing, they're talking about exaflops, exabytes of disk, and on the order of 100 petabytes of memory. And the reason they're not talking about exabytes of memory is all high-end supercomputers cost no more than $200 million. And the memory cost has gotten to be so big, such a dominant cost on the machine, that they're not going to be able to get exabytes of memory, even though I think there are people out there that would like it. So, why are people going to the extreme scale? It's the whole bigger, stronger, faster thing. Is you have more compute cycles and more memory. You can get faster turnaround time, and more often, what people want is they want to have more accurate simulations. And so that in a nutshell, is the driver for supercomputing. Okay, so the Petascale, I already mentioned, arrived in 2009. The first Petascale machine was the Los Alamos Roadrunner machine. It was a Linux compute cluster, except for it was all accelerated by PlayStation 3s. And so they took a whole bunch of PlayStation 3s and connected one to every Linux node. And as your simulation was running and you got to some very complex portion, you would take the routine and send it down to the PlayStation, which has a whole bunch of compute, let it solve that piece, and then when it was done, go back up to the Linux machine and have it continue the simulation. That was a monster to run on. You had to have 3 different compilers, 3 different sets of programs to effectively use the machine. These 2 machines, this one down here, the Oak Ridge Jaguar machine, was the #1 machine in the world until a few months ago. And the Kraken machine are 2 pretty conventional machines. They're both made by Cray. They're both, let's see, not quad-core, but hex-core Linux boxes, essentially. And it's taking the supercomputers that you have at your home university and just scaling it up to be very, very large. In this case, 216,000 total cores. This one here at Jülich in Germany is based on the IBM Blue Gene technology, which is different than the Cray ARC that we're on. This is a low power technology where you have to have lots of the cores to be able to get up to the same scale. So it's also an interesting petascale machine. So I said Jaguar was the #1 machine in the world until a few months ago. The new #1 machine is China's Tianhe 1A machine. And so the reason China's machine is so interesting is because it's all accelerated by GPUs. So where the Los Alamos machine was a real pain to program, the Chinese machine, this has a chance, right? Where before you had to have 3 compilers and you had to know how to write PlayStation code. Now you only need 2 compilers. You need something to run on the Linux compute nodes, and then you need to accelerate all the rest of your code on GPUs using CUDA or OpenCL. But that's a much more tractable problem. So I think this really looks like it's the future of computing, and it's the springboard to the exascale. And so the reason why is because if we were to take what we're doing right now and say, let's take this technology and scale it up to try to make an exascale machine, first off, it would cost much more than $200 million. But second off, the energy cost of such a machine would be about 100 megawatts a year. Now, the reason that's such a big deal is every megawatt a year costs about $1 million US. And so the energy cost of trying to create an exascale machine would be about $100 million a year just to operate. So that's too much, right? We need to have a power budget on the order of, at most, 20 megawatts a year, $20 million. That's still a big power bill, but it's maybe a little bit more easy to swallow. And so the key thing about GPUs is they provide a lot more compute per watt than the standard Linux compute cluster technology ARC. So exascale is a big deal. This is part of the community that's working on the exascale. And the reason it's a big deal is because about a dozen communities have come together and said, if they could get exascale computing, they could change the world. They could do predictive science. And the communities are the climate community, the fusion community, and others. And they've all said, if we could get this level of computing power, we could solve the problems we want to solve. And so as a result, the computer science community has come together and tried to decide, to figure out the best way to build this machine in a way that's going to be 20 megawatts a year, less than $200 million, and so on. Okay, so let me bring this back to visualization. we have a lot of increased computing power. The obvious outcome is we're going to have a lot more data. And so then visualizing all that data becomes a problem. There's really 4 axes to think about. The first axis is, as we have a lot of compute power, we're going to have very high resolution meshes. Right now we look at meshes that are on the order of anywhere from 2K cubed to 10K cubed. So that'd be from just a few billion cells per time slice to a trillion cells per time slice. They may get bigger yet. And so we have to think about how can we load that much data, process that much data, render that much data, and make a result that's worth looking at. So high resolution meshes is one way. Another way is we're going to have a lot more physics. If you have this much compute power, you don't just need to have routines that work at this physical scale. You might have routines that work at a coarse scale and other routines that work at a very fine scale. And you need to be able to fit all those together, and there'll be lots of variables and lots of data to look at from all those variables. Large number of ensembles. One way that people want to use this machine is rather than run one very high resolution simulation, they want to run many low resolution simulations. And then we have to, the data from these ensembles is going to be the same in toto as you would see from one high resolution mesh, but it's going to require very different visualization techniques to be able to understand what's going on in all those ensembles. And then once you give people big disks, they want to fill it up, and you end up with very high temporal frequency data. So these are kind of the 4 axes of changes in data that we're going to see as a result of increased computing power. So why does visualization work? Visualization works because we have this incredible ability in our brains to be able to look at pictures and be able to either identify trends or detect anomalies. And so by making pictures like this, we're tapping into this great hardware we have. And so when you start thinking about really big data, visualization is a very effective way for us to be able to understand that big data. It's not the only way. It's part of the bigger, one piece in the bigger ecosystem. There's statistical techniques, there's lots of analysis techniques, but visualization is a very important one for allowing us to understand big data. Okay, so in a nutshell, large data visualization comes down to 2 incredible challenges. The first is that we have to be able to reduce the complexity of the data. If we have very noisy data, some turbulent simulation where there are millions or billions of features in this data set and we put them all up on the screen, it may look really cool, but we may not learn about it. So we need to have techniques that allow us to reduce that complexity. The other challenge is, assuming that we know how to do this, we have to have something behind it that allows us to process the large scale of the data. So if someone puts a petabyte in front of you, or in the future an exabyte in front of you, how are you going to be able to look at all of this data? And so an important piece of this is the speed of the response is really important. And so I put up this fuzzy term that we all love to use: interactivity is important. And so interactivity may mean that someone asks a question, you'll be able to get a result in a minute's time. It may mean that you have to be able to spin something around in front of somebody at 30 frames a second. I mean both of those things when I say interactivity. But regardless, if someone wants to ask a question and it takes weeks to answer the question, by the time you get the answer, they'll probably forgot why they asked the question in the first place. You have to be able to get the results to them in a timely way. And so the large data visualization community right now, the way that we try to get people results to reduce their complexity in a timely way is through parallelization. Okay, and so how do we parallelize it? Right now, our community actually mostly just uses brute force parallelism. The idea if there's a parallel simulation code, it writes data to disk. By the way, I'm not a PowerPoint wizard. I'm a PowerPoint average guy. If I was a PowerPoint wizard, I could put up millions or billions of processors here. I'm not that good. So when you see these 10 processors, think of millions or billions of processors. But the idea is it writes a whole bunch of data to disk, and then as a post-processing activity, we have visualization programs and analysis programs that will partition the data over their processors, read them in, store them in memory, process them, and then render them. And so that's been a great arc that we've been on for the last 10 years. With petascale computing, we're seeing large barriers come up in terms of I/O bandwidth. And at the exascale, we're going to see additional barriers come up in terms of data movement. The power costs are going to constrain data movement. And so the community, there's been a lot of active research on these issues before, but the community has put a lot of effort now into looking into these smart techniques that are going to allow us to overcome the I/O barriers and the data movement barriers and still allow us to do the visualization analysis that we expect. And so what are these smart techniques? One of them is processing data in situ, i.e. our visualization routines become libraries that get compiled into the simulation codes and they produce the results on the fly. Multi-resolution techniques, so this is much like Google Maps where you have course data and you can dive in and dive in and dive in until you see the real original data. Out of core processing, so you process the data in pieces and never have to store it all in memory. And then data subsetting. Much of the data may not end up in the final picture. Why process that data in the first place? And how can we organize the data so that we can access the data that we do want to see efficiently? Okay, so for our community, to the simulation folks, we're certainly an enabling technology, and so it's really important that we deploy tools to them. And so I'm going to talk for a few slides about what the visualization tool community looks like, and I'll talk about an exemplar visualization tool, which is Visit. I don't really want to give a promo about Visit, but I want to talk about what the elements are that go into these tools. I think the community right now, when we're talking about large data visualization, it's all open source. And so what you see is you see dozens of institutions, multiple dozens of people working together on making products that the simulation community can use. We in the visualization field like to think that we add value in 3 ways. The first is we allow people to explore their data and come up with scientific insight. The second is a confirmation use case. People have run calculations thousands of times. They're running it 1,001st. They just want to make sure the train didn't go off the tracks. And the third is communication. So that's making movies, images for PowerPoint, and so on. And so those use cases, the people who are visualization experts, they make movies, they do communication. The people who are simulation code developers, they're doing confirmation. They want to make sure that their algorithm didn't change anything. And the people who are running the simulations, the people who are out trying to learn something with these simulation tools, these are the people who are trying to get scientific insight, who are trying to understand what the simulation is telling them. So this is quite a large community. This tool has been downloaded, I think, over 200,000 times. And so there's a lot of people who are in this space trying to look at very big data sets. How am I doing on time? Good? Time? What's that? I'm done? I kept looking back. Okay, great. Great. So I think actually that's a good enough place to end. You're saying I'm done with time. Yeah, great. Thanks for your attention.
But there is time for a couple of questions.
Okay.
So do we have any questions for him? You've stunned them to silence.
That happens.
We have a question here.
Yeah.
So you described Visit. What does Visit actually do?
Yeah, good. So I had another slide. So I went a little long. Visit is, if I look on the next slide, it's like the pair of the name. Because you hear Visit, well, first off, it's cheap. And second off, if you Google it, you'll never find Visit on the But certainly the tool is only partially about Google. The tool is about enabling insight and looking at something. And so they're still trying several uses. One is to people just want to bring the simulation to a cake and say what happened in this region. Another is people want to do analysis, comparative analysis. Another thing is they want to do exploration. Another thing is they want to do communication. So they turn to, and that may have been the question. The other problem is the node data income. So it's a framework for parallel data processing. And if there's some over 100 algorithms.
Yeah, we need to get him on there.
On a variety of, variety of mesh types, variety of algorithms, being that the users can then go and dynamically decide which algorithms they want to apply to look at their data. Okay, great, thank you.
Okay, thank you.